This is the ninth lecture of Module 4. Today we will have a discussion on static Kramer drive. This is the basic circuit configuration of a static Kramer drive. A static Kramer drive consists of a slip ring induction motor whose speed is to be controlled, a transformer, and a combination of a diode rectifier and an inverter. Here, the wound rotor induction motor or slip ring induction motor is fed from a three-phase power supply, and this is the input power. This input power is converted to mechanical output and mechanical power output, and the remaining power, which is not converted to mechanical power, is available in the rotor circuit. So to feed the rotor power or slip power back to the supply mains, we are using this setup because since the slip power has a frequency which is different from that of the supply mains frequency, it cannot be fed back to the source directly. Here in this example, the supply mains frequency is 60 Hz. So the rotor frequency will be different from that of the supply frequency. Rotor frequency is equal to slip into supply frequency. So we have to change the we have to change the frequency of the slip power, and then it can be fed back to the supply. For that purpose, we are using this converter circuit. Here the slip power is given to the diode rectifier, which converts the slip power to DC, and the DC link voltage of the diode rectifier is VD, and this is an inductor LD. ID is the DC link current, and this is a load commutated thyristor inverter which operates at a firing angle which is greater than 90 degree. Always the firing angle will be greater than 90 degree, greater than or equal to 90 degree. And the DC terminal voltage of this inverter is VI. So VD and VI. And the three-phase terminals of the inverter is given to the transformer. The transformer is having a turns ratio of N2. Here the wound rotor induction motor is having a stator to rotor turns ratio of N1. So the output of the transformer is given back to the supply mains. So this inverter will be operating at a frequency which is equal to the supply mains frequency. So this inverter will be converting the frequency of slip power to the supply mains frequency. So these are the conclusions. A portion of the rotor AC power is converted to DC by a diode bridge. The control rectifier working as an inverter converts it back to AC and feeds it back to AC source operation. Then let's have a brief analysis, mathematical analysis of the circuit. Here the DC link voltage of the diode bridge is equal to VD, and the output voltage of this thyristor converter is VI, VD and VI, diode bridge, output of diode bridge and output of inverter circuit. So let's write the expression for VD. The output voltage of diode bridge is VD is equal to 3 Vm by pi. That is the basic equation. 3 Vm by pi is the output voltage of three-phase diode bridge circuit, bridge rectifier. Here Vm is the maximum value of voltage, input voltage. So the input voltage to the diode bridge is the rotor induced EMF. So rotor induced, so 3 by pi into Vm maximum value is equal to root 2 times RMS value of the line voltage, RMS value of the line voltage of rotor circuit. So root 2 into VL RMS. Again, line voltage is equal to root 3 times phase voltage. So by substituting that, root 2 into root 3 times phase voltage. And this phase voltage is nothing but the phase voltage of the rotor induced EMF. So we are going to represent the rotor induced EMF in terms of stator input voltage. So we have to consider the slip as well as the turns ratio, stator to rotor turns ratio of the induction motor. So we face the per phase value of the rotor induced EMF is equal to S into stator voltage, stator phase voltage divided by the turns ratio. That is equal to 3 root 6 SB by pi N1. So this is the equation for VD, that is the output voltage of the diode. Next, the output voltage of line commutated inverter. This line commutated inverter is in fact a controlled rectifier which operates in inverting mode. So the equation for the output voltage of line commutated inverter, that is Vi, is equal to 3 Vm by pi cos alpha, where alpha is the firing angle and Vm is the maximum value of three-phase input voltage of this converter. This Vm indicates the maximum value of the line voltage. So maximum value of line voltage is equal to root 2 times RMS value of line voltage, and line voltage is equal to root 3 times phase voltage, and all these are the voltage at transformer input terminals. So here we are going to represent this voltage, that is the phase voltage of the transformer input terminals, in terms of the transformer output terminal voltage, that is the supply voltage. In terms of supply voltage, we have to represent this. For that purpose, we have to consider the turns ratio of the transformer. The turns ratio is N2. So root 2 root 3 into, instead of V phase RMS, we are representing this in terms of the main supply voltage, per phase supply voltage. This V is the per phase supply voltage. So V by N2 into cos alpha. That's equal to 3 root 6 V by pi N2 into cos alpha. Now we have the equations for Vd and Vi. Next we will apply Kirchhoff's voltage law in the DC link. In this law we are going to apply the Kirchhoff's voltage law. So for writing Kirchhoff's voltage law, we have to consider Vd and drop across the inductor and Vi. But here we can neglect the drop across the inductor. So assuming that the inductor is an ideal one, we are going to write the Kirchhoff's voltage law. But here we are neglecting the drop in the inductor. Neglecting the drop in the inductor, we have to consider Vd and Vi only. So Vd plus Vi is equal to 0. That is Kirchhoff's voltage law of this DC link. So we are substituting Vd for Vd and Vi. Vd and Vi substitute. After substituting, we will get the expression as S is equal to minus of N1 by N2 into cos alpha. So this is the basic equation that governs the operation of a slip power recovery scheme or static Kramer drive. So what is the inference of this equation? So here we can see slip can be controlled by controlling the firing angle alpha of the controlled rectifier or inverter. N1 and N2 are fixed values because these are the turns ratios of induction motor and transformer. These are fixed values. So the only variable is alpha. So by controlling alpha, we can control slip. That means we know that slip is equal to omega ms minus omega m by omega ms. So for a fixed frequency supply, by controlling by varying the value of slip, we can vary speed of the rotor, speed of the induction motor. So here, for that purpose, we are going to control the slip of the induction motor, and in order to control the slip or vary the slip, we have to control the firing angle alpha. And another thing to be considered is that this inverter will be always operating, or this converter will be always operating in inverting mode. That means the firing angle alpha will be always greater than 90 degree. So if in this equation, if alpha is greater than 90 degree or greater than or equal to 90 degree, slip will be always positive. For alpha greater than or equal to 90 degree, slip S will be always positive. And what is the meaning of slip is positive? Slip is positive means speed of the motor is always less than synchronous speed. That means using this drive, we can operate the motor only at speeds below synchronous speed. That means slip is positive. And by varying alpha from 90 degree to 180 degree, S can be varied from 0 to N1 by N2. If alpha is 90 degree, S is equal to 0. If alpha is equal to 180 degree, S is equal to N1 by N2. But another thing to be noted is that we will not be operating or varying the value of firing angle up to 180 degree because of some other reasons. That is for safe commutation of inverter thyristors. That is, we have to ensure that in a particular link, that is, in the case of this inverter, the thyristor pairs in one limb should not be turned on simultaneously. That means if this thyristor is to be turned on, we have to ensure that this thyristor is completely turned off. So for that purpose, for safe commutation of inverter thyristors, we have to restrict the value of firing angle alpha to 165 degree. That is a safe value. So we can say that the firing angle alpha is varied from 90 degree to 165 degree instead of 180 degree. So the maximum value of alpha is 165 degree for a Kramer drive. So slip can be controlled from 0 to 0.966 N1 by N2 when alpha is controlled from 90 degree to 165 degree. Now let's see how to design the transformer that is used on this side for a particular operating condition or for a particular application. That is, here we are going to design or choose the value of transformer turns ratio N2. How it's done? So we have the expression for slip S is equal to minus N1 by N2 into cos alpha max. But for the lowest possible speed of this motor, for getting the lowest possible speed of the motor, the slip of the motor will be at the highest possible value. That is the maximum possible slip at the minimum possible speed is equal to minus of n1 by n2 into cos in alpha max. The maximum value of firing angle alpha is equal to 165 degree. So from this equation, we can write the equation for n2 as transformer turns ratio n2 is equal to minus of n1 by s max into cos alpha max. So for a for according to our requirement, according to the required maximum value of slip, we can choose the appropriate value of turns ratio of the transformer. This is how the transformer is designed. Next, let's write the expression for the torque developed. For that, let's neglect the losses. So the slip power PR, we know that the equation for slip power PR is equal to SPG, and that is equal to the slip power means power coming here, and that slip power is rectified, and that power is passed through the DC link. So the DC link power is also equal to slip power. So DC link power is equal to VD into ID or VI into ID. Both are equal. So SPG is equal to VD into ID is equal to VI into ID. So let's take VD into ID. So mechanical power developed is equal to PM is equal to 1 minus SPG. This is a familiar equation for us. We have another expression for PM, that is PM is equal to T into omega M. That's also familiar. So omega M is equal to omega ms into 1 minus s in terms of synchronous speed and slip. So let's equate these two equations. So we will get PG is equal to T into omega ms. So we can write the expression for T. So T is equal to PG by omega ms, that is equal to, here PG equal to VDID by S. So PG is equal to VDID by S into omega ms. That's equal to, we are substituting for VD that we have already derived. That is 3 root 6 V divided by pi into N1. And here there is a term S also. So S in the numerator as well as in the denominator get cancelled. So this is the final equation. This is the equation for torque. So in the equation for torque for a Kramer drive, is torque is proportional to ID. That means the torque developed in the motor is proportional to the DC link current. That means if you have to control the torque of the motor, you have to control the DC link current. That is a basic concept. Now let's consider the torque speed characteristics. So as we have already discussed, the firing angle alpha is controlled between 90 degree to 180 degree, because firing angle alpha is always greater than or equal to 90 degree for the inverter. So the first torque speed chara is for alpha is equal to 90 degree, and that is the torque speed chara for natural speed, the highest possible speed. Again, if alpha is increased, the speed will decrease. Speed goes on decreasing. But here we can see that the maximum torque capability is also decreasing along with the increase in alpha. Next, we will consider the closed loop control of static Kramer drive. The static Kramer drive is the same. The only difference is that there is a feedback loop. There is a current speed control loop and as well as a current control loop. Here the speed is sensed using a speed sensor, and the actual speed is compared with the reference speed or speed command, and the error signal is given to a speed controller. The output of the speed controller is given to current limiter. The current limiter uh, gives us current command, the value of reference current ID, DC link current ID, and the actual DC link current ID as well as the reference current are compared, and the error signal is given to the current controller. And the current controller output is given to the firing circuit. The function of the firing circuit is to uh, produce appropriate value of firing angle according to the command coming from the current controller. So by varying the value of firing angle alpha, we can control the speed of the uh, induction motor. So when firing angle alpha is controlled, what happens? The amount of slip power that is taken from the rotor circuit and fed back to the mains is controlled. The amount of slip power is controlled by controlling the firing angle. When slip power is controlled, the speed of the induction motor is also controlled. In the next lecture, we will discuss the static Scherbius drive. Thank you.